Anyway, it's time for the next presentation. Lunch will be a little bit delayed because we were actually a little bit delayed when we started, but not very much. So this time it's Juanmi Gonzalez, who is assistant professor here at DTU in compute.
Well, first of all, I would like to thank Christina for inviting me to this interesting workshop. Yes, I'm Juan Miguel Morales. I work in DTU in the Department of Applied Mathematics and Computer Science within the Dynamical Systems section. And within this section, I'm one of the few people that work, of the several people that work on energy stuff. The title of my presentation is Operation Research Model for a Smart Energy System. And within this broad topic, I'm going to focus on applications more closely related to cities. Before I go into detail, I would like to say that most of the applications that I'm going to present here and most of the techniques are carried out within this newly established research center, which is called CITES. CITES stands, as you can see, for Center for IT Intelligent Energy System in Cities. And it has been funded by the Danish Council for Strategic Research. There are many partners from the university side and from the industrial side involved in this major research center. And I think, as far as I know, that Siemens is one of the partners of this project, This is the outline of the presentation. First, I will try to motivate as best as I can why we do the things that we do, why we think that what we do is interesting, and it's not only relevant for a scientist, but also for society. And then I must admit that I have a background more oriented toward electrical engineering. However, what I like the most about my job is mathematics, how to find novel mathematical solutions to address problems in the energy field. So you will probably hear during my presentation names like stochastic programming, robust optimization, just to give you a hint of the kind of techniques that we are developing and that we are using to address the challenges of the future energy systems. Well, I guess that we are all aware that there has been a remarkable increase in the amount of weather-driven renewables that we have lately integrated in the global power generation mix. But what I would like to highlight here is that this increase has been just spectacular in the case of Denmark, because Danes, they have very clear goals in this regard. In fact, the Danish government has two major ambitious goals. They have a final goal, which is that Denmark would like to become completely independent from fossil fuel energy sources by 2050. And as a stopover toward this major goal, they would like their power and district heat system to be fully based on renewable energy sources by 2035. So what does this mean for people like me, that like mathematics to solve problems? It means that we're going to have to change the way we think, the way we operate and plan current energy system. We're going to have to go from what we call a deterministic philosophy, where we believe that all the parameters and all the information affecting my problem, the decision-making problem, is perfectly known, to a philosophy where everything is stochastic, is uncertain, where the parameters affecting my decision-making process are uncertain. So we're going to have to go from deterministic tools to what we call stochastic or robust optimization tools. Any energy system that you may think of, gas system, district heating system, a power system, is normally operating in two stages. First, we have what we call, it's a short-term planning stage, what we call the scheduling or the dispatch of the system. This stage occurs, for example, 1 day in advance, or a little bit closer to real time, or before 1 day in advance. But the major idea here is that this stage is important for those big production assets, big industrial consumers that need to have an advanced planning to reliable adjust their production levels with sufficient time in advance. This short-term planning phase is also important for those people that are in charge of maintaining the security of the different energy systems, for example, EnergyNet Deco for the power system, because they would like to know in advance that the energy transactions that are taking place in their networks are going to be feasible. And if there is a problem, if they are going to have a problem afterwards, this problem is going to be small enough to deal with it easily. Then we have the actual operation of the power system, of the energy system in real time. And this balancing stage is becoming more and more important today because we're integrating more weather-driven renewables. Weather is uncertain, and as such, we are going to have to make more adjustment during the real-time operation of the power system, of the energy system, to compensate for the energy deviation caused by these new forms of energy sources. This is what we used to have in the past. We used to have big production assets, a fairly predictable demand, and the result was that most of the costs of operating our energy system were captured during the dispatch phase of the system, while the cost of balancing the energy system during the real-time operation were comparatively lower, much lower. But now, as we integrate more and more renewables, what is going to happen is that the share of the cost of the balancing cost within the total system cost is going to increase remarkably if we don't do anything to prevent it from happening. How do we prevent this from happening? Well, we are going to have to put a lot of flexibility in our system to compensate for the variability introduced by the weather-driven renewables. We are going to have to increase the flexibility from the production side, from the consumption side, from the way we are interconnected with other energy systems, and also, and this is particularly important for given my work, on the way we operate this energy system, on the tools that we are using to operate them. So flexibility is a must. And by now you are probably wondering where cities come into this, how cities come into this big picture. Well, very easy, because cities account for around 60 and 70% of the global energy consumption and greenhouse emissions. So if we are going to transform, if we want to transform our energy system into more sustainable, smarter energy systems, this transformation is going to happen in cities, or has to happen in cities. Now, what I'm going to do is to put you several examples of the things that we are doing in my section about how to increase flexibility from the different stakeholders involved in this problem. For example, how do we increase the flexibility of operating an energy system? Well, here I'm going to illustrate two operational paradigms. What I call a myopic operation. Here we have the dispatch phase and the balancing of our energy system. And basically, this is what we are doing right now. We are dispatching our system and then balancing our system in an independent way, in a separate manner. We, for example, say today that the wind power production at a certain point in time tomorrow is going to be, I predict, 50 megawatts. Then I dispatch my system based on this single value prediction, on this deterministic prediction. However, there is another way to operate our system. Is what I call the preemptive operation of the system. What we're going to do in this case is to use much more information about what is going to happen, about what it could happen in the future during the balancing operation of the power system to improve my short-term planning of the system right now. So I'm not only using the deterministic prediction saying that the wind power production at a certain point in time tomorrow is going to be 50 megawatts. I'm going to use also information on how wrong I could be, or how fast the wind speed is going to change. And introducing much more information now, we can make better decisions as a whole. This is just to illustrate the concept. Here, this figure, I show here the expected cost of operating a certain energy system. This is a realistic case. Okay, this expected cost is what we could see it as the long-term cost of operating the system as a function of the wind power penetration level for the two different operational paradigms. The green line is the myopic operation, where we don't make use of all the information available today, and the preemptive operation where we make use of probabilistic information about my renewable energy sources. What we can see is that from a certain level of wind power penetration, if we continue using these myopic operational tools, the cost of integrating these renewables is going to dramatically increase. However, if we are able to use in a smart way the information that we already have, we're going to be able to continue decreasing, to continue benefiting from integrating more wind power production. Of course, we can take this green line, we can make this green line coincide with this orange line, for example, investing in more flexible capacity. But the point here is that by using these more efficient operational tools, we're going to be able to delay investments and then to make some savings. Okay, now an example of what we're doing from the perspective of the production, of the producers. And here I'm bringing the paradigmatic example of a flexible producer in Denmark, which is a combined heat and power plant. A combined heat and power plant, which are all over Denmark and very close to cities, are production units that can produce both electricity and heat. How? This could be an example of, this could be an illustrative example of what a combined heat and power plant may consist of. For example, we have a gas turbine. The gas turbine can produce electricity by itself, but also the residual heat in the gas can be used to produce steam. The steam can also be produced by biomass, for example, by burning biomass. And then part of the steam can be stored in a heat tank to provide district heating to the city, or can be also bypassed to a steam turbine to produce more electricity. What is interesting about this combined heat and power plant? It's interesting because, first, it's a system that integrates several energy commodities and services: gas, electricity, and heat. So maybe we can take advantage, if there is any correlation, any interrelationship between these commodities. For example, it turns out to be that if the electricity price is high, or if the heat demand is high, then the electricity price tends to be high, and then the gas price tends also to be high. If there is this interrelationship between these energy commodities and services, we can take advantage of it, taking them into account in our operational models, and then to increase the benefit from selling electricity in the market. Okay? And what is that makes our combined heat and power plant particularly flexible? Basically, the heat tank that we have here, because unlike electricity cannot be stored easily in big quantities. Heat can be stored in the form of hot water very easily. So we can make use of this heat storage to interchange between electricity and heat. For example, I can store hot water in the tank during those periods in which the electricity price is low, and then use the heat accumulated in the tank to provide district heating to the city, and use the rest of my equipment to produce electricity and sell it in the electricity market at a higher price. However, this problem is very complex. It's very complex from a computational point of view. Why? Because it includes a lot of sources of uncertainty. The heat demand is uncertain, the power prices are uncertain, the gas prices are uncertain, etc. But also because it's dynamic. It's dynamic in the sense that, for example, we may have a gas turbine that has some limitation regarding the ramping rate of the gas turbine, minimum uptimes, minimum downtimes, etc. But also we have to keep track of the content in the heat tank. So what we are doing here is to use methodologies that are more suited for this kind of problem that are so complex. And just for you to hear the name, we are using here what we call robust optimization combined with linear decision rules. And this is a methodology that is able to capture, to take into account all the uncertainty sources that we have in the problem, and while we are capturing also the dynamic of our system. Okay, now just to finish, I'm going to put a couple of examples from the consumption side. Now we are going to picture ourselves in a probably not so far future smart city where we are going to have a smart meter. Everybody is going to have in their home a smart meter and a smart charging, a smart controller that is going to decide on our behalf how much we are going to consume based on what? But of course, based on the electricity price at that time, but also based on other factors that could affect my consumption. For example, the outside temperature. If I'm using an electrical heater, then I will be willing to pay a high price of electricity if it turns out that outside the temperature is very low. It's very cold, right? But also other kind of data, like wind speed, solar irradiance, that one way or another could affect my consumption behavior. But what is the problem? The problem is that we are very small. So we have to join forces because we are going to have to coexist and to compete against big production plants, big industrial consumer, against other consumers that are located in a different city or in a different country. So we have to join forces. So we believe that in the future, we will have an entity that we can call an aggregator that is going to aggregate the consumption of these small consumers and to trade our flexibility in the wholesale energy markets where these major transactions for electricity take place. So one thing that we are focused on right now is how to develop from the complex behavior of each consumer, how to come up with a very simple model that can simulate the behavior of a cluster of smart consumers. Because these wholesale energy markets, where people coordinate major transactions, cannot interpret complex models. They only interpret simple models. This is just an example. This is a real example from an experiment that took place in the Olympic Peninsula in the United States. Here, the black line represents the consumption behavior of an aggregation of 27 households that were flexible, that were responsive to price, to electricity price. What we try to do is to develop very, very simple models out of very complex data, out of big data, to track, to capture the consumption pattern of the aggregation of the loads, of the small loads. And just to finish, the last application we are working on is that we go lower into the hierarchy. Now we focus on a possible flexible load, which is, for example, an electrical vehicle. Okay, so we buy an electrical vehicle, and then we can collect data about the driving patterns of the EV users. For example, here we have data representing the trips starting at a given minute of an EV user. This EV user, for example, what we can see from the data is that tends to take the car around 6, 7 in the morning, probably because he or she is going to work. And then it also performs a lot of trips around 15 p.m., right? Because probably he or she wants to come back home. So what we can do is, based on this data, we can try to model the driving behavior of the EV user. Like, for example, here, what we have tried to do is to capture the probability that the EV user will start a trip at a certain point in time. We can capture this information, we model it, and then, based on this information, we can design a smart charging strategies for our EV user, based on what I said about the probability and the electricity price, for example. Here, just to give you an example, I represent the level of charge of the battery in our EV, in our electrical vehicle. For example, if it turns out that the battery is almost full, then we are not going to charge except in those hours where the electricity price is very low and before there is a high probability that the EV user starts a trip. But if the level of charge in the battery is very low, is almost depleted, then I'm going to charge almost always, except in those cases where there is a high electricity price, so I'm not interested in paying a lot, and the probability of starting a trip is 0 or very close to 0. By doing this, in an experimental setup, we have been able to save approximately around 19 and 47% of the electricity procurement cost without taxes, which are very high in Denmark. Also, we can even increase our savings if we allow the electrical vehicle to inject power back into the network and to sell this power. Not only charging, but we are also allowed to discharge our battery. Okay? And in this case, we can even make money using an electrical vehicle. So just some concluding remarks. I'm going to summarize the main line of thread that I have followed during this presentation. We are integrating, and we want to integrate more weather-driven renewals into our different energy systems, and cities account for more of the global energy consumption, so they are going to play a major role in this integration. This will mean that we will have to change the way we operate our energy systems, and we plan our energy system at all geographical scales, ranging from the small electrical appliance, washing machine, electrical vehicle, to a whole continent, Europe, going through cities, of course. And we believe, at least in the group where I belong, we believe that we already have the mathematical methods and the operational research methods to be able to guarantee or to support this transformation. So that's it. Thank you.
Thank you, Juan Gonzalez. I know according to the time schedule, it's lunch now, but it's really important for us to get some thoughts and feedback from you. So I'll invite you to stay for another 10 minutes to just do that. But before we address questions, comments, and so on for these two fantastic persons, I would invite you again to talk to one another, reflect on what did you find inspiring in these two presentations, and can you see any connections to things you do or between Siemens and DTU? So please talk to one another.